I wanted to get this one on film, a little bit more comprehensive than what we did in class. If if we look at this thing, we want to factor the top and the bottom. The bottom one's pretty easy to factor. X times x minus 2. The top one's a little bit more complex to factor because of um, the nature of the cubic here. If we've got negative x plus 6x squared minus 5, okay, it's negative x cubed, sorry. Um, the really only way we can look at this is to decide whether this thing is factorable through the rational root theorem right now. So I got to find my values of um, what we call p, which are the factors of that 5, so plus or minus 1, plus or minus 5. And then the same thing over here for q, be plus or minus 1. So then we've got all our p over q's. It's a pretty small list. P over q, um, we're going to go plus or minus 1 over 1 or plus or minus 5 over 1. So plus or minus 1, plus or minus 5. That's our list. So now we're going to do the synthetic division, and we come up with, negative 1, and there'll be a 6, a 0, and then a negative 5. Just kind of start wherever you want to, I guess, with these four values, whichever one we use. I'm going to try, I kind of just thinking ahead. It's not a very big um, polynomial here in regards to how many terms you have, and if I start putting a 5 in there, it kind of looks like maybe these values are going to get really large. So I'm going to try either 1 or negative 1. Let's just try 1. I'm going to bring down my negative 1. Gives me negative 1 there. It gives me 5. Give me 5, 5, 5, and that's really nice. It gave me 0. So well, I do have a 0 here. This thing does eventually factor to at least, right now, x minus 1, and then this will be negative x squared plus 5x plus 5. Okay. Now, if you're a person that likes to deal with factoring this thing here, this trinomial, with a being positive, you may want to take that negative out front of everything and go the opposite of x minus 1, and then rewrite this as x squared, be minus 5x now, minus 5. And now you start thinking, what numbers will multiply together to give me negative 5 and have to give me negative 5, and there aren't any that really do that. So what's going to happen is that you're going to use a quadratic formula to factor this. Quadratic formula. Okay, and it's going to provide us two additional zeros, but they're going to be irrational. And we could write them out. It's not going to be too hard to do that, and we could completely fully factor this cubic. Okay, but I know that, and hopefully this is something that you guys start to pick up on as well, that it doesn't really make a whole lot of sense to do that, because when we are looking at rational functions and trying to graph and gain all the information that we need to graph them, the only time that we really need to factor the top or really look at the top is for finding zeros, and for seeing if there's common factors up top and the bottom. And I know that when I factored the bottom, there were no irrational factors. There were no like x minus radical 2 or x minus radical 3s or anything like that that would cancel with something up top. Okay, so I know that I don't need to go any further with this. If we did, I guess kind of maybe proving my point even more here, using the quadratic formula, you go opposite of b, so it'd be 5 plus or minus 25 minus 4. A is 1, C is negative 5, then all over 2a, so it'd be 2. So we get 5 plus or minus, now I get 25, plus 20, so 45 over 2. So it's going to give me 5 plus or minus 3 radical 5 over 2. So what happens is that now I've got 5 halves, I'll write it this way, plus 3 radical 5 over 2, and I have 5 halves minus 3 radical 5 over 2. Those end up being the additional zeros for, not the additional ones, but those are the zeros for that function, or that expression there. So what that tells me then is that this original numerator here, this original numerator would have actually factored to, I'll write it here in green, we had our negative, and then our x minus 1, and now it would be x minus this thing. So I'll put that in parentheses, 5 halves, plus 3 radical 5 over 2, and then x minus that thing, so 5 halves, minus 3 radical 5 over 2. And then the denominator is going to be this x over x minus 2. Okay, so these two things, this thing here in blue and this thing here in green, they are identical. But I didn't need to really go as far as what I did in the green one, because I knew that the only reason I'm doing that is the reason I'm factoring the top there like that is to see if there are common factors. And I know that that factor there and that factor there are both rational factors. They don't have any irrational numbers. They don't have any radicals. So because that happens, I know that when I got to this thing here, there really is no need to go this far. Okay? You can. There's absolutely nothing wrong with it, but it's more work than what's necessary. So I just wanted to explain that, make sure we all understand that concept. Again, that's the thing about this course is mathematically, can we do the work? I hope, but more importantly, can we understand the math to where when I start getting values and I know the next couple of steps, can I eliminate having to do maybe steps B, C, and D, because I know how they relate with one another, and I know that I'm not going to need, in this case, to factor this one that far, because I know the only purpose I have for that is to cancel common factors, and I know I'm not going to have them. That's, I think, one of the big things about mathematics that, as a teacher, I struggle with trying to get students to realize is not just to, blindly close my eyes and just start doing the math, but to, at every step, analyze the math, see what it's telling me, how does that save me work, what new work does that provide, that kind of thing. So we get to this, and remember the first thing is always to check common factors. So we don't have any of those, so that means you have no holes, no point discontinuities. Next thing I like to do is find vertical asymptotes, so that's when the denominator is equal to 0. So those components, x is equal to 0, and x minus 2 is equal to 0. This tells me a lot right here for things that we have to come up with later. Remember, we want eventually to find y-intercepts. Well, if I have a vertical asymptote at x equals 0, that means I can't cross that vertical asymptote, which means I can't cross the y-axis in the case. So y-intercepts, in this case, I'll have none. I like to do, you got some options. You want x-intercepts, you want y-intercepts, that kind of stuff right away. I'm going to go horizontal asymptotes and slant asymptotes first. And what we do with those is we always compare the leading terms. Okay, well, in this case, the leading terms differ, so the numerator is bigger. So what that tells me is I have to do is I have to go through the long division. X squared minus 2x is my divisor, and underneath is negative x cubed plus 6x squared plus 0x minus 5. And I remember when I think about things that go here to multiply by this divisor to get negative x cubed. So that's obviously negative x. Multiply gives me negative x cubed, and then plus 2x squared. We talked in class how I'm a fan of changing the signs and then adding straight down. I do my subtraction by adding the opposite. So those go away, and I get now 4x squared. Bring everything else down, 0x minus 5. I'm now going to multiply by a positive 4 to get this 4x squared, so that gives me 4x squared minus 8x. Again, change signs, and then add straight down, so those go away, gives me 8x minus 5. Now at this stage I can stop with the long division because this degree of 1 is smaller than that degree there of 2, and that tells me that this is my remainder. Now in the whole grand scheme of things, that remainder doesn't really matter for finding slant asymptotes because slant asymptotes, the reason we're finding them is that they show me what the end behavior of my rational function looks like. And if I write my equation as negative x plus 4 plus my remainder of 8x minus 5 over my divisor of x squared minus 2x, that's fine. But when x gets really, really, really big, this number approaches 0. So I have whatever this is plus basically 0. So it's really just whatever this is. So that's why the remainder doesn't matter when finding the slant asymptote. It's only the quotient that we're interested in. So that is my slant asymptote. Okay. Now, our goal is to see if we ever cross the slant asymptote. So we take our original polynomial, or not polynomial, rational function, sorry, which was negative x cubed plus 6x squared minus 5 all over x squared minus 2x. And that was f of x. But I think it's best maybe in this situation to remind ourselves that f of x is just the function notation to tell us that the y values all pass the vertical line test concept. So let's just change it to y, and that maybe makes it a little bit more simple for us in regards to what we do. We know that this is ultimately a nonlinear system of equations. So if those two y's are equal, in the event that these two curves do cross each other, it's going to happen where those two expressions are equal. So I'm going to take negative x plus 4 and set that equal to negative x cubed plus 6x squared minus 5 all over x squared minus 2x. Now at this stage, what we're going to do is we're try to solve for x, because that's what we do with any other system that we ever come across, is we try to solve for x, and that will tell us the x coordinate of where these things cross. If I can find a concrete x value, then I plug that back in to find the concrete y value of where these two curves cross. And that's what you do with any system of equations. Find x. Once you find it, plug it back in and find y. So as we go through this, and you saw a couple maybe examples in class where the algebra might present new ideas. If I start multiplying by the LCD here, so x squared minus 2x here, that's going to cancel and cancel. Come over here and do that, x squared minus 2x. The new algebra tells me that I essentially have x squared minus 2x times negative x plus 4 equals negative x cubed plus 6x squared minus 5. Now, as I start doing this, because this is implied multiplication, so I've got to do that multiplication, whatever this yields, whatever this provides, if it provides me with something squared in the end, and my equation is now squared, a quadratic, well, that implies that I need to factor it and find my solutions that way. So that would imply that I cross my horizontal asymptote maybe, or my slant asymptote maybe twice. If everything kind of breaks down to a linear equation, that tells me when I solve it, I'm going to cross my slant asymptote one time. But whatever the new line provides me, there's implied math involved. There's implied algebra steps of solving maybe multi-step equations, maybe solving a quadratic equation by factoring, maybe a cubic equation by factoring. Maybe it's quartic or quintic that is yielded here, just depending on what these things were up here. And then maybe that's factoring by using the rational root theorem. So we're kind of at the stage in this course and through mathematics in general, your algebra knowledge, that you really know everything that you need to progress through any problem that I present you. It's just, do we understand, do we know and remember the implied processes that are required when we see a certain expression or a certain equation. So when I see this, that tells me I need to multiply out, so I get negative x cubed, and then I'll multiply and get 4x squared, and then plus 2x squared, and then minus 8x. On the right hand side gives me negative x cubed plus 6x squared minus 5. So what I was talking about there a moment ago before I did the multiplication is that I know that those are going to cancel out. I know that this 6x squared there and this 6x squared are going to cancel out. And I'm left with now a pretty simple one. I call it a multi-step equation, but it's only a one-step equation. But it provides me math that now I know what I'm supposed to do. I'm supposed to solve for x. Well, if this was some quadratic here, I still want to solve for x. And how do I solve quadratics for x? I use factoring tools, factoring techniques. At this stage, I'm solving for x, divide both sides by -8. I get x to be 5/8. So it tells me that I do cross my slant asymptote. I do cross, and it's at x equals 5/8. Well, in order to find out where that actually is, in regards to the y value, we'll take that 5/8 and we'll plug it back in to this stuff up here. Okay, now it gets messy because of that fraction, but if I'm thinking about f of x, and now we're plugging 5/8 for x, so f of 5/8 is what we're really looking at. I want to have up top negative 5/8 cubed plus 6 times 5/8 squared minus 5 all over then 5/8 squared minus 2 times 5/8. That's exactly what this original rational equation looked like, a rational function I should say, looked like, but now I just take an x and replace it with 5/8. You can evaluate that. You can go through and multiply that all out. You know, getting real nice values for my denominators and stuff like that. So I'm not changing this to a decimal. Let me take a minute and I'll do that real. All right, so 5 cubed is 125. 8 cubed is 512. So we got that. Again, so now plus 6 times 5 squared is 25. 8 squared is 64. And then I've got minus 5. And on the bottom I have 25 over 64 minus, I'll just go ahead and rewrite this as 10 over 8. But now you got common denominators, the LCD probably here. Maybe the best thing to do would be, 512 I think is going to be your LCD for the numerator. It's going to be the 64 be LCD for the denominator, but overall when I want to work with this stuff, 512 is going to be the best thing to change all your fractions to in regards to the denominators. But you can go ahead and figure that out and find that fraction. That's a process. We can also, like we said in the past, go ahead and just evaluate this with my calculator and it'll give me my decimal back. I think that decimal becomes like 3 point something, 3.625 or something like that. But we'll see that here in a moment when we graph this thing. So we do know we crossed the horizontal asymptote. I want to find x-intercepts. Okay, so x-intercepts again are when the numerator is equal to 0. So if you remember your numerator, we had factored that to, I think, x minus 1, x minus 1, and then the x squared minus 5x minus 5, and we had this negative out front. But when I set that equal to 0, I get x equals 1 as an x-intercept, but I get this thing here. Remember that thing? When that is equal to 0, x squared minus 5x minus 5 was equal to 0. I'm not going to do all this work again, but if you remember, it should have been 5 halves plus or minus 3 radical 5 over 2 is I think what we end up finding. Those are your two other x-intercepts for this curve. You would probably, when you graph this thing, you want to probably put those in decimal form. But then all we got to do is we got to go through and set up our x, y axes. We had a vertical asymptote at 0 and 1 at 2. So there's that one. We've got 1 at 2. We had our slant asymptote at negative x plus 4. So I go find my 1, 2, 3, 4 is my y-intercept there. A slope of down 1 over 1. So it looks something like that. Okay. Just some key things to kind of come up with here. We had, an x-intercept of 1. So there's my 1. There's an x-intercept. And we've also got some other x-intercepts. I don't know necessarily what these are right now. I haven't changed those to decimals. Let me do that real quick. So we got 2.5 minus radical 45 over 2. Okay, so one of these becomes negative 0.85, and the other one is 5.85. All right, so negative 0.85, so if that's 1, so there's a 0 there. And then this one, 5.85, 1, 2, 3, 4, 5. 0.85 is a 0 there. We also knew, so those are my zeros. We also knew that we didn't have any y-intercepts, but we did cross the horizontal asymptote, or sorry, the slant asymptote at 5/8. So 5/8 would be, kind of maybe there. You see that's a little bit above 3 in the y direction. So that's kind of what that curve looks like. Now, this is actually enough points to really gain a good curve. We know we should be restricted by these two asymptotes kind of in that region, all right, because of where that x-intercept of negative 0.85 showed up. We also know over here, as I move to the right, I should kind of eventually get closer and closer to this asymptote. As I move to the left here, I'll eventually get close to that asymptote. But now here in the middle, we cross the horizontal and we have an x-intercept. So the idea is that this curve should do something like that, and then like that. Now, obviously, smooth curves, we got a lot of undulations here, but that's the idea. Now, if I go to, like, say, GeoGebra or Desmos, maybe I'll use Desmos. Let's see here. Oh, it was loaded. All right, so I'm going to type in, we had up top, negative x cubed. Try to find that original function we had. Negative x cubed plus 6x squared minus 5. And then divide that by x squared minus 2x. And we should end up mimicking everything that we found by hand here in our graph. Kind of try to find the best way to jump back and forth here, show everything. We know that if I plug in just my vertical asymptotes, x equals 0. You see that blue line there being your vertical asymptote, and that kind of makes sense kind of with what's going on here. We also had a vertical asymptote at x equals 1, or not 1, what was it, 2? 2. And that is mimicked again. We had the slant asymptote of negative x plus 4. And we see now in that orange curve that is all mimicked. Okay, so we do have those asymptotes correct. Okay, and we can, kind of go down this way, and you see we're going to never cross that slant asymptote over there. We're never going to cross it up here in the long run, but we do cross it relatively close to 0, 0 if we look at this orange asymptote and the red curve. We do cross. And what I like about Desmos is that I can actually click on that, one of the curves, and it shows me the intersection of that curve and everything else. So 5/8 is 0.625, and 5/8 evaluated inside this function up here. If I put 5/8 everywhere I see x, will eventually give me 3.375. Okay, which we could have found using it as a fraction earlier by going through all that common denominator stuff that I was showing you. We also see that here, there's your negative 0.85 as an x-intercept, and this one should be 5.85. There you go. This one should be 1. So that's all the information we need to do that.